Hello, everyone. Um, I want to keep working with the moment of inertia just long enough to get the parallel axis theorem out there, and then we'll show an example problem if time allows. Okay, so the moment of inertia says if I have some funky shaped object, maybe that's a head of a troll. Anyway, that this object will have a center of mass someplace. And we can calculate a moment of inertia for the object about the center of mass just by taking the integral of all the distances from the center of mass dm. So wherever a mass is located, we're going to find it relative to the center of mass of the system. Which is great and all, unless maybe we can maybe make the best of that. If this corner down here is our axis of rotation, so what we need then is axis of rotation. For most normal shaped objects, we have a whole list of what the center of masses look like, but let's recognize that what we need to do then is take the integral of the axis of rotation. So I need to find wherever the center of mass is, and for once I drew a vector when I should not have. And that's going to be squared. We're going to add to it the distance, and again, not squared. So this is a generic, looking system when our axis is located at distance d, for distance, away from the center of mass location. So, what we need to do for our integral is not do it. And here's what I mean. In pen format. So here's what I mean. I'm going to take this, and I'm going to break it up into r center of mass squared dm. Just going to FOIL this all out and get 2 r center of mass dm integral, and then get the integral of d squared dm. So let's pull this together. Taking the integral of r squared about the center of mass, where all the objects are located, is really just the I center of mass I started with. This one here, the d is a constant. It goes from the axis to the center of mass. So this allows us to see this as d squared, the integral of dm. So in other words, d squared times the sum of all of the masses. And this term in the middle is fun, because if you do the integral, oops, I missed a d up here. Doesn't really matter for the argument, but I should at least be correct. I get r center of mass dm. And this is taking every object's individual mass particles and then taking it from the center of mass. And it's the center of mass not squared. So it's a case of saying the top half of the integral of the object above the center of mass, that's going to be positive. The bottom half, center of mass section, is going to be negative. So this integral just takes itself right to 0. Because of the power of the center of mass. So we wind up with the parallel axis theorem, which says that as long as everything is along the same axis, and I'm trying to find the moment of inertia for a new location, then what I have is, if I can find the formula for the I center of mass about the same axis, what I need to do is add a term that is also related to the same axis. So as long as everything is spinning around the same long axis, parallel axis theorem is great. So let's do a quick example from the book that I think is a wonderful example. In fact, I had used it in my class for years before it finally wound up in print. So, I like it. So let's get rid of that. I'm in blue ink, fine. Let's do 2 bars that are fashioned together. So it's really one shape. So if you want to think of it that way, we can get rid of the whole thing. We can do this and have some kind of T bracket thing. But ultimately, it helps to think of them as two rods. And let's rotate them about the end of this one. Okay. So in this case, I know that by looking at a table or looking it up in the internet, that the eye's center of mass, not center of mass, sorry, the eye of a rod around its end is equal to 1/3 ml squared. I suppose in this example then each of these rods are going to have a mass and a length. Which we might as well make equal. Using the parallel axis theorem then says, take this T-shaped object and, well, it's not even a parallel axis theorem, it's actually just the definition of moment of inertia, summing up all the r squareds with the dm's. And what we get then is I'm going to be summing up the eye of the rod plus the mass of the other rod. This is so tough to do without pointing. Maybe what we need are subscripts. Okay, so I'll be referring to this rod as 2 and this rod as 1. So the first thing I do is use the known moment of inertia for the rod around its end axis of rotation. And then I want to add from rod 2 the mass of 2 coming into L squared. But I want to make it clear that this last point has less to do with the moment of inertia, the parallel axis theorem, and more to do with the definition of the moment of inertia, which just says, as long as everything is rotating around the same axis, you are allowed to add them up. Now, sometimes we have to use the parallel axis if we don't have a good representation for the shape. But in our condition, we do, because rod 2 is really nothing more than a mass at the end of rod 1. So this thing has a moment of inertia, which is 1/3 mass 1 length 1 squared plus a mass which happens to be 2 plucked at the end of length 1. Why am I treating a rotating rod as if as just a point mass? Because this second rod is not rotating in and of itself. It is stuck to the end of a rotating rod, number one, so mass number two just moves with mass number one in the same big circle. So that's a quick introduction to the parallel axis theorem, with a little bit of an example of how it can all come together.